In the last lecture, we spent a lot of time looking at intermolecular forces. These are the electrostatic attractions between molecules that are responsible for getting them to stick together in the liquid state and the solid state. In this lecture, we're going to look at certain properties of liquids to get a better feel for how intermolecular forces influence the properties of liquids. There are a whole raft of properties for which intermolecular forces are important, and I've given an incomplete list here, but these are things that we're going to cover in this chapter. In the last section, we focused primarily on boiling point because that's really a very good proxy for the overall strength of the intermolecular forces. In this section, we're going to look at viscosity, surface tension, and capillary action, all of which are strongly dependent on the intermolecular forces. In the later sections of this chapter, we're going to look at things like heat of vaporization, the heat of fusion, and the vapor pressure of liquids. Viscosity is a property that defines how easily a liquid can flow. To get a mental image, imagine liquids that are highly viscous. Think about pouring honey or maple syrup. Or here we have a picture of two different motor oils. So you know if you go to pour honey over your pancakes, of course you kind of have to wait for a while for the honey to flow out of the bottle and onto the pancakes. Right? If you had a same container of water and you turned it at the same angle that you would for pouring that honey, all of the water would immediately flow out of the jar. There are a couple of ways you might measure viscosity. One of them might be kind of like this experiment here to see how fast a liquid will flow through a thin tube. The faster it flows, the lower the viscosity. Another way, which we'll see a video of in just a minute, is to drop an object through a liquid, like a ball bearing through a cylinder of the liquid, and see how long it takes for the object to move through the liquid. And the slower it moves through the liquid, the more viscous the liquid. Now, at the molecular level, what's going on with viscosity is for the liquid to flow, the molecules have to slide past one another. Okay, so there's a couple of things that will make a liquid more viscous. As the intermolecular forces get stronger, it's harder for the molecules to flow past one another and the viscosity goes up. It's also true that as the temperature goes up, the molecules have more kinetic energy and therefore can move past one another more readily, and the viscosity goes down. So we see that viscosity increases with stronger intermolecular forces and decreases with higher temperature. Let's consider 4 different liquids, the molecules of which I show here. I want you, to the best of your ability, to make some predictions about which of these molecules are likely to be more viscous and which less viscous. In fact, why don't you try to rank order them from the least viscous to the most viscous. Please pause the video, make your predictions, and then come back and we're going to watch a video where we see the answer. Okay, welcome back. Let's now take a look at a video that was produced by the chemistry department here at Ohio State University and see what is the answer.
Let's look at how intermolecular forces affect viscosity. Here we have tubes filled with hexane, ethanol, water, and glycerin. Hexane is a nonpolar substance and only has London dispersion intermolecular forces. Ethanol has some mild hydrogen bonding, water has a lot of hydrogen bonding, and glycerin with 3 OH groups has tons of hydrogen bonding. Inside each of these tubes is a ball bearing. So I'm going to flip this and we'll see how fast they move. You can see that hexane falls the fastest, then ethanol, then water, and glycerin takes a really long time to fall due to the hydrogen bonding.
Okay, so the order is something like this. Really, we saw that one of them, the glycerol, or sometimes it's called glycerin, was much more viscous than the other 3. If you look closely, you'll see that the hexane was the least viscous. And in that demo, it would seem that water was a little bit more viscous than ethanol. Although if you look up the actual viscosities, it's actually the opposite. But the two are actually very, very close to one another. So the question is, why? I mean, hexane is actually the largest molecule here, but being a nonpolar molecule, it only has dispersion forces. And because of that, it's pretty easy for the molecules to slide past one another. So we expect substances that only have dispersion forces to a first order to be not very viscous. Of course, when the molecules get very, very big, like they are in motor oil, that changes the story a little bit. Then the dispersion forces can get relatively strong. The molecules can get tangled up with one another. But as long as the molecule size isn't wildly different, only dispersion forces gives you lower viscosity. The other three molecules can all hydrogen bond, and that leads to considerably stronger intermolecular forces and higher viscosity. But the difference is when we look at the glycerol molecule, it can hydrogen bond in 3 different locations. So that makes it much stickier to the other molecules. It's a lot harder for that molecule to slide by another molecule because all throughout the molecule, it's forming hydrogen bonds. Water, being small and rigid, can form hydrogen bonds, but it's so small that it's a little bit easier for it to move past other water molecules. And ethanol is also, pretty similar to water. Now, we saw that the hexane was really not a very viscous liquid. We can see that as we increase the length of the hydrocarbon chain, the chains are getting longer, and therefore there's more dispersion forces, so the intermolecular forces are getting stronger. Also, these molecules have a lot of flexibility, and they can kind of pretty easily get tangled up. And so you can see that the viscosity goes up steadily. Now, this little water molecule, little, but it forms hydrogen bonds, it has a viscosity that's about 9 times 10 to the minus 4. So you can see it's in between nonane and decane. The bottom line is, large flexible molecules, even though they might not be able to hydrogen bond, will eventually become relatively viscous. Small, rigid molecules tend to have a lower viscosity depending on the types of intermolecular forces present. But when we go to molecules like glycerol, which are bigger than water and can hydrogen bond in more than one place, we see that the viscosity goes up pretty dramatically. Here, let's look at the viscosity of water, 0.9 times 10 to the minus 3. Ethanol, 1.1 times 10 to the minus 3. And then ethylene glycol, right? We already saw water and ethanol are pretty similar. But if we put another OH group, so this ethylene glycol, that's what the antifreeze that you use in an automobile is made out of. Its viscosity is 26 times higher than that of ethanol. So being able to hydrogen bond in more than one spot is important, and it causes the viscosity to go up dramatically. If we think about honey, honey is mostly sugar. The most prevalent sugar in honey would be fructose. And let's look at a fructose molecule. There's 1, 2, 3, 4, 5 different OH groups. Fructose can hydrogen bond in 5 different places on a molecule. And because of all of these hydrogen bondings, it really makes a lot of interactions with neighboring molecules, and that gives it a very high viscosity. Another property that depends on intermolecular forces is surface tension. If you think about a liquid, let's think about water, for example. And if you were to put water on, let's say, a newly waxed car or some other surface that was hydrophobic, it would form beads, right? And those spherical beads, why does it do that? It does that because it wants to minimize its surface area. And another way of thinking about that at the molecular scale is that if the intermolecular forces are strong, the molecules want to be surrounded by other molecules. They're attracted to them, and that force of attraction stabilizes the liquid state. So it wants to minimize the number of molecules that go to the surface, because a molecule at the surface, you see, it's missing some neighbors. And because of that, it's being pulled in some directions, but not others. And that really kind of actually exerts an inward pull on the molecule. So liquids that have high surface tension, they are going to want to form shapes like beads that have low surface area. If you have a low surface tension, then what a liquid might do is just spread out and form an even film, right? It might maximize its surface area. So that's what we mean by surface tension. And water, having strong intermolecular forces, has a fairly high surface tension. And here we see this water skipper bug, and because of the surface tension is why very light objects like this insect can walk on or float on the water. Now, a lot of times when we think about the behavior of a fluid and whether it's going to form a bead or do something different spread out, we actually have to think about a little bit more than just the forces within the liquid. Right? The forces between molecules in the liquid, we can call those cohesive forces. But the liquid, like that bead of water on a waxed car, is also sitting on a surface. And we can also think about the forces between the liquid and the surface. And those are called adhesive forces. The beading of water is one where the cohesive forces are much larger than the adhesive forces. But if we reverse the relationship, then the water would want to spread out. It would want to be in contact with the surface as much as it can. And that's exactly what happens in something like a paper towel. Right? The whole point of a paper towel is you want it to wick up the fluid. And the way to do that is to make the interactions between the paper towel and the water stronger or more attractive than those between one water molecule and another water molecule. Both cohesive and adhesive forces and the balance between them are really important in something we call capillary action. What is capillary action? So the idea of capillary action is that if you have a narrow tube, then a liquid like water will be drawn up the tube. Right? This is the basic principle that plants use to move the water against the force of gravity up to the outer leaves. Or think about an oak tree or a redwood tree. That tree has to move the water from the ground up a great distance, and it does it through capillary action. Here we can see the capillary action at work in a test tube, which isn't that narrow, right? But even in a test tube here, we can see that there's a meniscus. Right, and that meniscus has a U shape. The water is at a higher elevation at the surface where it meets the glass tube than it is in the middle, right? The U-shaped meniscus. And the reason for that is because the cohesive forces between water molecules are not as strong as the adhesive forces between the walls of the glass tube and the water itself. And you can imagine if the tube got very, very narrow, you could suck the water up the capillary tube. If you have the opposite situation, where the cohesive forces that hold the molecules together is stronger than the adhesive forces to the surface of the tube, as is the case here with liquid mercury, because with liquid mercury, the intermolecular forces are really metallic bonds. And you can't metallic bond to a piece of glass. So here we have weak adhesive forces and very strong cohesive forces. And so in that case, we get an inverted U meniscus. Well, that's the idea of capillary action.